All right, welcome back, Atlas. Today we're going to be starting a new topic series, essential topic number 3. I'm going to be looking at the equilibrium rigid bodies in 2D and 3D. We're mostly going to be concentrating on 2D for this module. So as always, we ask the questions, what problems do I need to know how to solve? So the things you need to know. We need to identify common connections and their associated reactionary forces. Okay, when we cut off the wall, the wheel, the pin, the joist, what is holding those two things together, essentially, is what we're asking. Okay, we also need to know how to draw a proper free body diagram. So all the reactionary forces, any of the length, any of the measurements, and the body itself need to be included in a free body diagram. And last but not least, we need to be able to calculate our reactionary forces using Newton's second law. So some of the forces in the X, the Y, and some of the moments about any point we like. I got a couple of diagrams down here at the bottom. If you haven't seen me use this yet, this is a physical. Oh, look at that. The green screen's messing with you. So we have a R here and we have an F. So if you draw one of these in real life, plans right here on the diagram, you'll never be questioning which, if the moment is positive or negative based on the force and the reaction arm you have. Highly recommend you get one of these. Make one of these. Okay, and then if you use the cross products, this right here, if we do X cross Y, that's positive. That's in the red direction. That remains positive. If you have any that go X cross Z, which is the blue direction, you're going to pick up an extra negative simply by doing the cross product there. Okay, keep those in mind for when we get into it later. Okay, so first problem is we need to identify the reactionary forces. So given the following 9 diagrams, draw the reactionary forces. I got something new for y'all. Check this out. We're going to use this slide and not my top-down camera. So without further ado, let's get into it. First problem, given the following 9 diagrams, we only have one here. Draw the reactionary forces. So first things first, we're going to draw our representative body. We're going to draw our externally applied forces. Keep that as F. On the right hand side, on the top, we're going to have B there. So it's a little bit tricky. Okay, it's attached with the pin. So let's just go ahead and put the pin in first. So if this is attached with the pin, we're going to have a BX and a BY. I'll show you why that might not be necessary later. But A definitely held on with a pin, so we can do AY and AX. Okay, so at connection point B, it's held on a roller to a pin. So let's draw the free body diagram of the roller over here. Okay, there's our roller. And we're not drawing the ground here, so we should have a reactionary normal force. So we'll call that normal of B. Okay, and because this roller is supposed to be attached to the body AB, we should give it the same forces, equal in magnitude, opposite in directions. So BX going to the left, and BY going downward. And if we go ahead and use Newton's second law in the X direction, we see that BX, and there's nothing else to oppose it, so we're going to call that equal to 0. So this guy does not exist, therefore this one does not exist. And so for this problem, we should only have 1, 2, 3 reactionary forces. Okay, move on to problem number 2. Same song and dance. We have a different shape here though. Our representative body, our externally applied load. At B, we have a pin, so we're going to go ahead and go BY and BX. At A, held on with a rigid wire of some type, maybe a rope. So we're only going to get one force here, so AX, and that is all she wrote. We got 1, 2, 3. Reactionary forces, only 3 in this diagram. Okay. We have 3 connection points this time, so we'll draw a representative body. AX. We have a BY here, we have a BX, and another CX. And you know what? I did something a little bit interesting here. On the AX arrow, I used a principle of transmissibility, which means basically that anywhere along this line, I can draw AX. Okay, and it doesn't violate any rules. So I probably should have just done something like this. Make it clear. Okay, and notice that here and here, the reaction point is coming from the left and coming from the right. When I draw a free body diagram, I don't try to guess what's happening there. I just assume that AX and CX are both going to be positive. Okay? And I say positive because I'm operating under the assumption that this is my positive convention here. So positive X, positive Y, positive moments. Okay, so if AX, if I need an AX, I'm going to assume that it's positive and to the right. And if I need a CX, I'm going to assume it's positive and to the right. The math will tell me later on whether I was right or wrong in my assumption. But to make things easy when I'm drawing free body diagrams, just make them all positive, make your life easier. So for this one, we have 1, 2, 3, 4 reactionary forces. Okay, a little bit different of a scenario here. Have the same body. An externally applied load here. And again, we can use the same trick I used in the first one. I can say that there is a Y, a B, Y, and if somebody says, hey, those are attached with a pin, you need an X component, I'll go ahead and put those in there. But if I go ahead and draw, let's call these A and B, and we draw the normal force of A and the normal force of B. We copy down A. Oops, that's the wrong direction. Remember, they need to be equal in magnitude, opposite in direction. So our AX should be this way, and our AY should be downward. Same thing with B, BY, and BX. And if we do the Newton's second law on either A or B, we see that AX is equal to 0. Nothing opposes AX, therefore BX is 0 and AX is 0. So the answer to this problem is only 2. All right, let's move on to number 5. A little bit different of a scenario here, but we got this. We have the skills. Okay, externally applied load. I always copy those down first. At point Charlie, I'm just going to go ahead and only include CY. I'm not going to do CX. We proved it twice already. Not really important because we know that C is attached to a pin, but it's attached to a roller, and the roller only gives us one force that opposes the perpendicularity of the plane which is touching. At point Bravo, we don't have that. We have a pin, so we're going to go ahead and put B, Y, and B, X in. Alpha is at a different angle, so I violate my rule here of not going positive, but it's going to come from the body out towards A, and we're just going to call that tension of A. Because it's not in the X direction, it's not in the Y direction, I can't really do that. The picture doesn't give me enough information to tell me what angle it is, so I'm just going to assume that this portion here is in tension, and so I'm going to call it tension, and it operates at point alpha, so I'm going to call it tension of alpha. So that's how I'm going to read this here. Tension of alpha. And I just say alpha because when we're speaking to each other and we see A, B, C, sometimes we get a little bit confused, so I substitute in other words so that we're clear on what point I'm exactly talking about. Okay, so let's go ahead and circle our reactionary forces. 4, and so our answer for this one is going to be 4 reactionary forces. Okay, interesting. Now we have an angle given to us, so let's go ahead and draw our representative body. And let's start with alpha. Alpha is a roller on its side now, so I'm going to assume that we only get AX. B is a pin, so we're going to get a BX and a BY. Externally applied force F is attached with a Bravo. So, answer to this problem is we're going to get 1, 2, 3 reactionary forces. And we don't need to deal with the force F and Bravo. Or this is beta. Don't have to deal with it. Answer's 3, and we can move on. A couple more problems to go through here. This one is pretty interesting. This one people get wrong a lot. So check this out. We have a representative body at an angle. We don't know what the angle is. We have an externally applied load here, F. And we have a pin at A. So go ahead and draw in our positive AX. Oops, that's not X, that's Y. And AX. At point Bravo, this is where it gets a little bit interesting. Because the body is not touching the floor is directly touching the body. And so we can treat point Bravo like a roller. So it gets a force that is perpendicular to the body. There. Okay, and I'm going to call that normal of Bravo. Normal of Bravo. Okay. So for this problem, we have 1, 2, 3 reactionary forces. A little tricky, not too bad. Okay, let's go on to number 8. One more after this, and then we'll bid you adieu. Okay, so got my body here. I have 4 externally applied loads. They're all the same magnitude. They're all called F. Okay, now the hard part. Let's start with alpha. Alpha is a roller attached to a pin that's touching point alpha. Same song and dance like we did in the first 2 problems, where we're only going to have one force here. And that's going to be alpha of Y. I could call it normal at alpha, but I'm assuming that at point alpha, this is acting at a 90-degree angle, because everything looks 90 degrees to me. And then at point Bravo, we have a pin, so a BX and a BY. So our final answer here, 1, 2, 3. We don't have to worry about any of these externally applied forces. Okay, only the reactionary forces. Okay, last but not least. This one trips up students as well. That's why it's in here in 8 and 9. Okay, so we have an interesting body. It's not just a rod anymore. It's got a little bit of an angle on it. Okay, we always copy down the externally applied forces first. And at point Bravo, this is that pin and roller combo thing that we discussed earlier. So we're only going to need a BX. And at A, we have an AY, and we have an AX. That's it. We could go through the whole song and dance of having this guy again. Oops, I shouldn't draw this. Normal at B, and BX acting on the roller should go equal in magnitude, opposite in direction. So we'll have a BX, and yeah, so this is why we see that the sum of the forces in the X direction, BX, is going to equal negative NB. Okay, so answer to this problem, 1, 2, 3. And I think that's all I have for y'all today. Next time we're going to be calculating the reaction forces. So first lesson, we went through and we found all of the reaction forces that are possible. Actually, you know what? I lied. One thing I realized right now that I missed. Let's do one on the fly here. Let's do this. I didn't do the standard cantilevered beam. Okay, so let's check this one out. Let's do this. You know what? This time I'm not going to call it force. I'm going to call it P. I don't know why we use P, but we do. Okay, so if I wanted to find the reaction forces for this cantilevered AB, I'm going to redraw my beam AB. Go ahead and label these. Copy down my reactionary or my externally applied load, P. And at Bravo, we have nothing. It's a free end. This is like, you know, you go to a pizza shop and there's a sign that sticks out of the wall. There's nothing there. All of the reaction forces that are keeping this bar in equilibrium, this beam, are going to happen at A, the building, the thing it's stuck into. Okay, and so if I have a rigidly attached beam, I'm going to get 3. I'm going to get an AX, I'm going to get an AY, and I'm going to get a moment. Okay, which way do I draw the moment? Well, I'm going to return to this picture where I have positive X, positive Y, and positive moments. And I'm going to assume that my moment at alpha is that direction, because this and this match. Okay, and if you didn't catch this, this was moment at alpha. Okay, that's how we pronounce this M sub A. All right. Hope you learned something today. If you did, go ahead and leave a like. Consider subscribing. It's a brand new channel. I'm aiming this towards my unborn son. We're 39-ish weeks now along, so he can come any day now. Definitely going to be a Christmas baby. So if you want to see us grow and you want to invest something in the channel, you know what to do. All the stuff I've been using on this journey today is going to be linked in the description, so you can check those out. Support me a little bit if you want. But that's for me. I'm out. Peace out, everybody.